It's been about 13 weeks since school started. We've lost about 13 brain cells. But we've learned a lot. Heat transfer plays a crucial role in everyday lives, from industrial processes to daily tasks like cooking and home heating. One important process is free convection, where fluids like air or water naturally transfer heat across surfaces without the need of external forces like pumps or ceiling fans. This process is vital for applications such as heat exchangers, the cooling of electronics, or managing building temperatures.
Have you ever burned your mouth drinking hot coffee? Or has your cup ever gotten cold way too fast? These everyday experiences are actually great examples of heat transfer in action, specifically free convection. Let's dive into how this process works. In this experiment, we'll explore how changing the exposed surface area of a container of boiled water affects heat transfer through free convection and uncover the factors that influence the temperature changes.
In order to create a controlled environment, our system has been set up to mirror a perfect insulator. For this reason, we have decided to use thermos containers and assumed no heat loss from the water evaporating and a constant heat capacity.
Assuming the thermos containers are well insulated, we can assume that conductive heat transfer is negligible, and only heat loss is due to convection through the top surface. This system can be described by a simplified form of the general equation for temperature, with Newton's law of cooling.
For this experiment, you'll need various thermos containers of varying open diameters, a timer, 2 cooking thermometers, a measuring tape, some water, and an electric kettle.
Start.
Sweet.
In this experiment, we have 2 thermometers, one measuring the temperature of the water surface and the other measuring the bulk temperature. The temperatures were recorded at 30-second intervals for each container.
We expect that thermoses with a larger open diameter will have more heat loss over the span of 5 minutes than those with a smaller open diameter. This hypothesis aligns with Newton's law of cooling.
The change in bulk water temperature over the 5-minute period was measured and plotted to investigate the heat transfer process according to Newton's law of cooling. The results shown in the figure demonstrate that the bulk temperature decreased over time, with the rate of temperature change higher for thermoses with larger exposed surface areas and lower for smaller surface areas. This suggests that heat transfer occurred primarily through convection at the exposed surface, consistent with the assumptions of the experiment.
Plotting the rate of heat transfer relative to the surface area of the thermoses, we see a slope that corresponds to the convective heat transfer coefficient of the water. According to Newton's law of cooling, we expect a y-intercept of 0, which corresponds to a closed and perfectly insulated system. The y-intercept we have plotted is positive, suggesting there is some heat loss due to the conductive heat transfer through the thermos's walls. The intercept suggests that the heat loss due to conduction through the thermos's walls is on the order of 40 joules per second. If we assume evaporation was minimal, the convective heat transfer coefficient is about 44 watts per square meter Kelvin.
In conclusion, this experiment confirms that surface area is key to how quickly heat is transferred in free convection, supporting Newton's law of cooling. Our data shows that thermoses with larger surface area lost heat faster, highlighting the importance of surface geometry in natural convection. These findings are valuable for improving thermal management in various fields, as increasing surface area can boost heat dissipation and energy efficiency. Overall, this study deepens our understanding of what affects convective heat transfer. Thanks for watching.